So although in certain cases we may not have the structure of a certain chemical compound for whatever reason, we can determine the percentages, so the relative amounts of the elements in that compound, and this information is very useful to scientists. So the definition of percent composition is the percentage by mass of each element in the compound. It can be determined from the formula of the compound and also from the experimental mass analysis. In other words, you'll be given percentages of the elements. So for example, let's say we have a hydrocarbon. So this is a compound just made up of carbon and hydrogen. You would take the mass of the hydrogen divided by the mass of the entire compound, multiply by 100, and you would do the same thing for the carbons. So in this example, we'll be determining percent composition from masses that the problem gave us. So we have 24.81 grams of a sample. We don't know what the formula is, but we know that we have this many grams of carbon, 4 grams of oxygen, 17.81 grams of chlorine. What is the compound's percent composition? So let's go ahead and calculate that out. So for carbon, we're going to take the mass of carbon over the mass of the entire compound. You can just write comp. Times it by 100. We're going to do the same setup for that oxygen. 4 grams of oxygen divided by the mass of the compound. Let me just write a line so we can tell the difference. Times 100%, and then again for chlorine. So for chlorine, it's 17.81 grams Cl divided by that 24.81. So I'm going to go ahead and multiply these out and see what we get. So I went ahead and divided the masses out. That cancels out the units for grams, and then you multiply by 100, and then you don't have any units at the end. These are the percentages that I got, and they all add up to 100. You can also determine the percent composition given a formula mass. So we're going to go ahead and do that. Here are some common fertilizers, and then the question is asking what is the percent composition of ammonia? So we're going to look at ammonia specifically. For homework, you can do these or just test out what you just learned by doing these other two. But let's go ahead and look at ammonia. So ammonia is NH3. So in order for us to find these percent compositions, we're going to first have to find the mass of ammonia as a whole. So remember we learned how to calculate formula mass? That's what we're going to do here. So here we have 1 nitrogen and we have 3 hydrogens. The mass of nitrogen, you go to the periodic table, you look at the mass, and that's what you're multiplying here. Is I believe either 14 or 1401, but let's just say 14. And then the mass of hydrogen is this one, I know it, is 1. Okay, so now we multiply that out. This one is just obviously 14. And then for hydrogen, I'm going to multiply it out and then add it all up together. So you get for the mass 17.024 grams per mole. That's the mass of ammonia. But we're going to calculate the percentages of first nitrogen and then hydrogen inside the ammonia. So for nitrogen, so percentage of nitrogen, it's 14 divided by the entire thing. The grams per mole cancel out, times 100. And then the same process for the hydrogens, which is 3.024, right? Because there's 3 of them. And then divided by 17.024 grams per mole times 100. Grams per mole cancels out, and then we just calculate this out. So once you calculate this out, you should get for percentage of nitrogen 82.2 and for percentage of hydrogen 17.8. And notice again that these add up to 100. So within any chemical formula, we can also actually extract some conversion factors from those formula. So for example, let's say you have just a simple one, H2. In 1 mole, right, this is H2. This is a molecule. In 1 mole of H2, I have 2 mole of hydrogen. So 1 mole of H2 is those molecules, right? Think of them like units. But when we look at hydrogens, like just trying to quantify how many hydrogens in general are in that amount, you use this conversion factor. So essentially they have inherent relationships between these numbers of the atoms and the molecules within whatever molecule you're looking at. You can also think of it as moles. So it translates directly. So if you have, right, because we can also say, like if we're going between these two, in 1 molecule of H2, I have 2 atoms of H. So this is where your knowledge about what molecules versus atoms are comes into play, because this is essentially what lets us interchange between the two. So this is another example. So you have 1 mole of CCl2F2. Within that mole of CCl2F2, you have 2 moles of Cl. So it's the exact same type of relationship as up here. And again, these relationships can be used to determine amounts, right, of elements or molecules. And they can also help us with percent composition. So again, think of a situation where you have amounts of elements within a sample, but you don't know the formula. So we actually have a process for this where we can determine the formula from that experimental data. And that is called the empirical formula. So we find the empirical formula from this type of data that we can collect. Now, when we find the empirical formula, this formula is the simplest whole number ratio of the atoms and of elements in the compound. So all it tells you is a ratio. So it doesn't necessarily tell you the full information for most cases, but it tells you a lot. So again, you can determine this from getting the analysis of the elements within a sample. And this is how we actually find the empirical formula. So there's kind of a lot of steps, and it won't make sense until you actually do it, but I'll just read the main points here. First, you convert any percentages to grams. So you're going to assume that you have 100 grams of the compound. So if you have percentages of elements, you assume 100 grams. If it's already in grams, like we saw earlier for percent composition, you just skip that part. From there, you go to moles. From there, you write something called a pseudo formula, and then you will divide by all the smallest number of moles. And then if you have numbers that are not whole numbers, you have to multiply by certain numbers such as 2, 3, and 4. So it's important to understand like the major steps, but what's more important is actually putting it to practice. So let's start off with the first step. We have a sample containing 1.71 grams of carbon and 2.287 grams of hydrogen. What is the empirical formula? So convert the percentages to grams. Do we have percentages? No. So we actually already have it in grams, so we just basically skip this part. So go to number 2. Convert grams to moles. Use the molar mass of each element basically to get to moles. So again, that's why I put the little mole map here. So we're starting off in mass, so we're trying to get to moles, so we're going to use the molar mass for that. So we're starting at step 2, and then I'm going to set this up. Grams of carbon in 1 mole of carbon, we have 12.01 grams of carbon. That's the molar mass. It just comes from the periodic table. And then for hydrogen, we have 0.287 grams of hydrogen. And the molar mass of hydrogen is 1.008. We'll cancel out the grams and then calculate the moles out. So I went ahead and calculated those out. I got 0.14238 mole carbon, 0.28472 mole hydrogen. So don't worry about sig figs right now. Like I said, it depends. So in this case, this problem doesn't really ask for it doesn't ask for a value at the end. It asks for a formula. So you'll see the answer that we get at the end. So our next step, we finished number 2. Our next step is to write a pseudo formula. So this is what we're going to do now. A pseudo formula means that you're going to set up kind of like a makeshift formula. Carbon goes first, and then we have hydrogen. You are going to write the moles that you got. So we have 0.14, I'm just going to write 2, and then 0.284. That's good enough. Yeah, so we use the moles as subscripts. We did that. Now move on to step number 4. Divide all by the smallest number of moles. So essentially this is our step number 4. The smallest number of moles is the 0.142. So we did that. And what we actually get from this is 1, right? 0.142 divided by 0.142 is 1. And then for hydrogen, when you divide that out, you get 2. So if your result is within 0.1 of a whole number, you round. In this case, we got exactly a whole number, so we're actually done by now. And this is our empirical formula, and a better way to write it is just CH2. So empirical formula. So I mentioned previously that the empirical formula doesn't necessarily tell us everything about this compound. It tells us the ratio of the elements to each other. So earlier, on the previous slide, we just got this empirical formula, right? What this tells us is that we have 2 hydrogens per 1 carbon. So you see how it's a ratio? And the molecular formula, what it actually is a multiple of the empirical formula. So this empirical formula could be C2H4, it could be C3H6. So it depends on whatever integer multiple that you get. In order to determine that small whole number ratio number, you have to divide the molar mass by the empirical formula mass. And in order for you to actually understand this pretty well, we're just going to go ahead and practice it. So let's say that we have a compound whose molar mass is 180 AMU. And we know the empirical formula is this. The empirical formula mass comes from the formula. So anytime you need to calculate empirical formula mass, you take the empirical formula, so CH2O in this case. You have 1 carbon, so that's 12, and I'm just writing this shorthand like fast. I have 2 hydrogens, so that's around 2 grams or AMU, grams per mole. Same thing. I have 1 oxygen, which is 16. When you add this up, 16 plus 12 is 28, plus 2, that's 30. So you see where they got that AMU from. And then it asks, what is the molecular formula? So first you determine the empirical formula. In this case, the problem already gave you the empirical formula. But if you don't have the empirical formula, you have to follow all those steps that we previously just did. And then you divide the molar mass. So they gave us the molar mass right here. So that's the molar mass right here on top. You divide that by the empirical formula mass. Now, when you divide this out, you're going to get a whole number. You're going to take this whole number, you are going to multiply the empirical formula by this whole number. So this is multiplied against that, multiplied against that, it's multiplied against that carbon. So that's where you're getting that C6H12O6. So this C6H12O6 is the molecular formula. So again, it's a multiple of our empirical formula. In this case, it's times 6. So Now we are going to go through an example where we have to first determine the empirical formula and then determine the molecular formula. So this is about as complicated as it gets. So if you have the rules for the empirical formula written out, bring them out and you can have them next to you while we do this, because I'm just going to do it from memory. So step 1, convert the percentages that you were given. In this case, you can see that they gave us all the percentages into grams. So you assume that it's 100%. So we're going to assume that we have 49.47 grams carbon, that we have 5.201 grams hydrogen, that we have 28.84 grams nitrogen, and finally that we have 16.48 grams oxygen. And notice, if you're ever confused about when you're given one of these problems and you're like, do I have to find the molecular formula? Like, what, like, how do I know what to do? Well, obviously, it's probably going to ask. But either way, just know that you will always have to be given the molar mass. If they don't give you the molar mass in the problem, there's no way that you can calculate the molecular formula from the empirical formula. The only thing you can calculate is the empirical formula. So we're going to go ahead with we did finish step 1, and now step 2 is to convert to moles. So same step here. And we are going to set that up. So I went ahead and set it all up and then divided by to get my moles of each of these. Now step 3 is to set up your pseudo formula. So I'm going to set it up over here just because there's space. And then we are going to divide for step 4 by the smallest number of moles. So this is both of these steps. So first is going to be carbon, then hydrogen, then nitrogen, and then oxygen. So for carbon, we got 4.12. For hydrogen, 5.16. Well, that's bad. Nitrogen, 2.06. And then oxygen, 1.03. Now, the smallest amount here is oxygen. So we're going to divide. And then 1.03. Now, you divide these out and then rewrite with those new numbers. So once you divide these out, this is what you get. Now, this is our empirical formula. So good job, we just found our empirical formula. If you can get this far, you're halfway there. Now, they're asking for the molecular formula. So we got this out the way, determined empirical formula, and then we need to divide the molar mass by the empirical mass. So first we need to find the empirical mass and then divide that into here. So here we have our empirical mass set up. It's going to be whatever the value is times the mass that you see on the periodic table. So I'm going to go ahead and write this out and then add it all together. So you should get 97.1 for your mass. So this is our empirical formula mass so far. So the molecular formula mass, I'm just going to say molecular mass, is 194.2, sorry. And it was in AMU, but we can just say the same thing. So we can just convert this to AMU. Remember, 1 gram per mole equals 1 AMU. So sorry, that was my bad. But what we're going to do next is we're going to divide our molecular mass, 194.2, by our empirical formula mass. Whoops. And then once you divide this, you find out you get, well, AMU cancels out, and then you find out you get 2. This number, we're going to take it and multiply it against our empirical formula. So I'm going to take this 2 and essentially multiply it out. So it's going to multiply out here, here, to every single element. And now what we will get for our molecular formula is C8H10N4NO2.